people will join later on. We'll make sure that the recording is working, so that we have a trace. We'll post it later on our YouTube channel. My name is Arthur. I'm a very quick introduction. I'm the president of the Quantum Computing Association of EPFL. It's a pleasure to welcome you and welcome ATOS for this presentation of their software package for quantum computing. So the ATOS has been active in the field for a while now, and we have the chance to welcome them for an introductory presentation on their full ecosystem, what they call the quantum learning machine. They'll talk about that in a minute. And also to give a kind of a tutorial of how to use their own platform and how to do quantum programming for everyone. A good part of this software stack is open source, so we'll make sure that you get all the link to practice yourself for these tutorials. And yeah, I'd like to thank a lot Mario, who's been dedicated to organize this with very much attention. So I'd like to thank all the team from ATOS, and without further ado, I let the speakers take the lead.
Yeah, just a few words. Thanks to you, Arthur, to give us the opportunity to organize this session. I would like also to say a warm welcome to the audience, and especially into the ATOS quantum world, because it's a real quantum world, ATOS quantum world. ATOS is one of the key, as you said, one of the key players in this domain. We already set up a strong relationship all over the world with university and research center by providing them on-premise QLM services, assistance, but also and now MyQLM. Okay, and we will talk about all this later on. I would like also to inform you that ATOS is a real active member of the Swiss Quantum Hub, and also last but not least, we are finalizing an agreement with the CERN to provide them an on-premise QLM. This is what I would like to say, and now I hand over to Xavier and Sabine for the presentation. Thank you.
Hi everyone, so maybe I can provide a short introduction on myself, and Xavier will too, and then we will present our overall program. So as Mario mentioned, so I work at ATOS within the Big Data and Cybersecurity division. And within this division, I work more specifically as a product manager for the ATOS Quantum Learning Machine, which is ATOS Quantum Simulator. Xavier?
Yes, and myself, Xavier Geoffret, I'm part of the same division as Sabine, and I'm leading quantum activities for pre-sales activity around quantum projects. So the presentation today will be in two parts. The first part is more a presentation of what ATOS is offering. I will do a short introduction on quantum computing, and then Sabine will dig into details about our offering. And the second part will be dedicated to demonstration and hopefully some interactive session. But at any time during this presentation, do not hesitate to either interrupt us or maybe put questions in the chat, and we will try to answer them as much as possible. So let's start first with a short introduction on quantum computing. I will keep it short because I think that most of you are aware of the situation, but just to explain you just to explain you why ATOS is positioned on this activity. So to be clear, and I like to start with that, we like to say that quantum computing relies on a promise, and this promise is to say that when quantum processors are available, they will be able to tackle some large and complex problems faster than existing classical computing solutions like the fastest HPC systems. And why I say why I say that, because if you look at the history of quantum computing, we have divided into three parts. The first part started a few decades ago, where there were essentially research activities around quantum computing. So this was the works from Feynman, and in 1994, Peter Shor has published a famous paper regarding the factorization of large semi-prime numbers with an algorithm that has its name now. And this is really this was really a huge theoretical and mathematical research activity. But all this activity was not backed by real hardware progress, and during many years this activity was a little slowed down because of the lack of progress. But things have changed recently. A few years ago, there were new processors that become available, and these processors, at the moment, I would say, I would name them prototypes of processors. They are what we call NISQ. NISQ stands for Noisy Intermediate Scale Quantum. They are NISQ in the sense that they are noisy. That means they are sensitive to noise. Their decoherence time is quite short. They are unstable, and they are intermediate scale in the sense that they cannot scale to a large number of qubits. So at the moment, what we have is devices that can scale up to a few dozens of qubits, and most of them are really, really noisy. But even with those these problems, the research activity on algorithms has demonstrated that we can take advantage of noisy processors, and we will talk later on about variational algorithms. And the third part of the history is the future. We do believe that there will be a significant progress in the hardware, so we can have no longer noisy qubits, but perfect qubits, probably made with a fault tolerance, and this will be the era of a fault tolerant quantum computers. But this is something that will occur probably in 10, 15, 20 years. In fact, nobody really knows if and when it will happen. But the important point is we are in the NISQ era now, and we expect to have commercial products, commercial QPUs available in the next 2 to 5 years. And what's important to understand is this processor will not replace classical processors, but they will act as accelerator of classical processors. So what we used to say to our customers, and this is also a message that I would like to carry to you, the processors are coming. The research on algorithmics is very intense and has proven results. We do have simulation capabilities, and we will show you later on these simulation capabilities. So it's time now to invest time and effort to be ready for when the processors are available. So really, it's time to invest time and effort now. Just to give you an overview of what the quantum computing can bring to the different industries, we have identified many use cases across various industries of what a quantum computing can bring as a speed up, and these different use cases can be grouped in several categories. You have an application related to combinatorial optimization problems, and we will discuss a little bit later about combinatorial optimization problems. So it can be applied to logistics, or to portfolio optimization, or to optimization of grid management, yield management. So this is something that you can find in every industry. You also have a category of problems related to a machine learning and the use of quantum to accelerate machine learning, and especially training of machine learning models. You have applications in the field of cybersecurity. I've talked a little bit about Peter Shor algorithm that is used in cryptanalysis. So there is a strong activity in that domain too. We have also many applications in the field of chemistry and material sciences that can be applied to many industries as well. It could be to discover new polymers, new batteries, or to define new drugs or nothing like that. We have also applications that are more specialized, for example, in finance or in oil and gas prospection or in drug discovery. So to explain a little bit some of these applications, for example, in chemistry, we have a very good algorithm like the variational quantum eigensolver, VQE, that is used to find the ground state energy of a molecule. And finding the ground state energy of a molecule is the key to define its properties just by simulation. And this algorithm, the VQE, is really interesting because it can take benefit from the NISQ processors because of its variational properties. So we will discuss a little bit about later. Another important field of application is pharmaceuticals. We are able, thanks to quantum computing, to do some virtual screening. So virtual screening is an important step in the drug discovery process to test the behavior of different, what we call compounds, so molecules that are targeted to be a drug in the future. So we can test virtually billions of molecules without doing any chemical experiment. I've talked a little bit about cryptography already, and just a really important point regarding cryptography. Today, most of the transaction and communication are using asymmetric keys algorithm, and those asymmetric keys algorithm are very sensitive to quantum attacks, just like Peter Shor's algorithm, and this is really critical. But we will see that the impact, even if it's potentially huge, the probability of happening in the short term is relatively low. So we will discuss it about later. So we have also some specific algorithm for the finance industry. And for example, when we are talking about different operation like trading strategies or option pricing, you can use a differential equation like the Black-Scholes partial differential equation that is derivative from the Schrödinger equation, and that can be used also, that can be simulated or used in a quantum processor. There are also other applications also related to machine learning, but okay, we'll talk about machine learning later. In the oil and gas prospection, there are many also application of quantum computing to speed up some part of the very computing intensive process, and especially in linear algebra, and with one of the famous algorithm, which is HHL, to do matrix inversion. But we have also very interesting topics, research topic regarding partial differential equation to solve also the simulation of the oil wells. A very important topic in terms of application is the combinatorial optimization problems. So combinatorial optimization problems are a class of problems where you have to consider a huge number of possibilities. And a very good example is the famous traveling salesman problem, where you have a salesman that has to travel across all cities once and only once, and he has to find the shortest path to optimize its route. And when you have only a few cities, this problem is solvable by hand. But if this number of cities goes above 20 or 30, you cannot consider all the possibilities. It's an exponential problem. So you have to find an approximation, and this is where quantum computing also can be helpful. So with some algorithm like QAOA, we're able to write the finding of the good approximation. And these algorithms have proven to be faster and more accurate than classical algorithms, even if they are not solving the problems. It's an NP-hard problem, and it stays an NP-hard problem. It cannot be solved even by quantum computing, but you can find approximation faster and more accurately. And the application for combinatorial optimization problems can be found nearly everywhere, from finding the best route on your GPS system, or grid management, power management, supply chain, logistics, flight scheduling, yield management. So there are many, many applications. And another topic of interest is how to use quantum techniques and quantum algorithm to speed up machine learning, and specifically to speed up the training phase of machine learning, either by porting existing algorithm to their quantum counterpart, or by developing brand new algorithms. So this is really a domain of research that is quite intense. So what is important to understand, I've shown you really rapidly many applications of quantum computing, but not all of them will become available at the same time. And on this slide, on this chart, it's not easy to read, but if you look on application on the right side, these are applications that will come sooner. And on the left side, you have applications that will come later on. And what you see, for example, on your right, you see chemistry. Chemistry is an application that is already available today because we are able, with existing algorithm and existing NISQ processors, to simulate small molecules. So as far as the number of qubits is increasing, the size of the molecule you can simulate is increasing too. But you can already, with the hardware we have today, we are able to calculate the ground state energy of small molecules. On the opposite, I was talking about cybersecurity and cryptographic algorithms. These algorithms, we already know that they require some perfect qubits. We cannot work with noisy processors on them. For example, in the case of the Peter Shor's algorithm, there were some estimation about how many qubits are necessary to be able to crack let's say a 2000 bit key, and the approximation is around 50 million of qubits. So probably this is you will probably need something like 50,000 qubits that are perfect, and to get one perfect qubit, you probably need to have 1,000 physical qubits. So at the moment, I said we are in the order of magnitude of dozens of qubits. Before we get to millions or dozens of millions of qubits, you may wait maybe 10, 15, 20 years. So cybersecurity is a major threat, but it's so far from us that the probability to happen in the short term is very, very low. So I wanted to finish this introduction by giving you some figures about what is the market today of quantum computing. To have ideas, on the top of the screen, you can see the investment that is planned for the next 3 years in major regions in the world, and you can see that the market value is above $6 billion for the next 3 to 5 years. Well, yes, for the next 5 years, with significant investment in many parts of the world. But if you look at the longer term, so I would say the next 5 years will be still the NISQ era, but if you look at the longer term, in the 20 years or more, when we will enter, hopefully, in the fault-tolerant quantum computing era, the size of the market is expected to be probably 100 times bigger. So this is a market that will explode in the next 10 to 20 years. And if you look at, this is why you get many well-known companies that are investing massively and specifically into hardware. You can see a few names that you are familiar with, like IBM or Google or Honeywell. Those companies are investing in developing quantum hardware. I will make a few comments about them. First comment, all these names that are here are American companies, US-based companies, and all these companies are trying to solve or to tackle this problem with a different technological approach. If you can see IBM or Google are chasing after superconducting qubits, where Honeywell is working on trapped ions, or Microsoft on Majorana fermions. But beside those very well-known names, you have other pure players, so smaller companies that are not, I would say, traditional IT companies that are dedicated to quantum research from scratch. And I've just cited a few of them that have raised more than $50 million fund in the past years. And you can see in the names, maybe you are familiar with some of them, like D-Wave or Rigetti. If you look at this name, I will make the same two comments. First comment, most of these companies are not US-based. That means that the race today has become worldwide. So you have investment and company doing research on quantum hardware everywhere in the world. And the second comment is regarding also the technological choices they have made. Here again, you have different technological choices like quantum annealing or photons or silicon qubits. So in summary, what we see is the race to get the first quantum processor has become worldwide, and the technology that will be prominent in the next years is not yet clearly defined. So there is no clear winner at the race at the moment, for the race at the moment. So this is why we do believe that it's a little bit early to invest in quantum hardware because it's not clear who will win the race, who will be able to provide the most scalable architecture and the most stable architecture in the future.
Okay, thank you, Xavier.
Yeah, Alex Sabine.
Thank you. So now I will explain a bit more how ATOS decided to get involved in this new technological shift, and to present how we decided to tackle this very broad topic of quantum computing. So it all started around 2015, when we saw those big irons getting into this race and trying to find the best hardware technological fit. What we decided was to rather position as a company that would help its customers get acquainted with this new technology, learn about it, learn how to program these new kind of computers, without having to wait for them to be available, accessible. So in order to do that, we built, so first we gathered some of the most brilliant minds on this topic around our CEO. So we've got in our quantum advisory board people such as Arthur Eckert, Alain Aspect, Serge Haroche, Daniel Esteve, or David Di Vincenzo. So these people helped us build a broad strategy to tackle this topic, and they actually gather quite frequently to review the strategy and help us reorient it, taking into account the latest developments. So this is our ATOS Quantum program that was launched in 2016, and that relies on 5 pillars. The first one is about providing our customers with a quantum programming platform that will help them train their resources to this new programming mindset and prepare their quantum algorithms for when NISQ accelerators are ready and are accessible. Then we also, as we saw that this topic was quite new for most of our customers, we also decided to provide expert consulting services to help them identify within their business use cases which use cases might benefit from a quantum speedup, and then to implement these use cases in the quantum world. We have a very specific positioning about quantum hardware. So we also decided to help our quantum hardware providers ecosystem build these new generation architectures. And we announced in 2018 that we would have our own NISQ accelerator within our portfolio by 2023. So we are actively working on that. Of course, in the process of training and guiding our customers in this new journey, we developed an in-house expertise on quantum algorithm, more specifically focused on variational algorithms, the hybrid quantum classical algorithms well suited for the NISQ accelerators that Xavier mentioned earlier. And we are also a cybersecurity company, so it's important for us to provide our customers with the right tools to tackle quantum computing, but we also need to help them protect themselves from the threats that might arise from this new technology. So we also invest in research on quantum safe cryptography. So in order to give you an overview of what has been achieved so far by ATOS in this field and what we are planning to do in the coming years. So as I said earlier, in 2016, we launched this overall ATOS Quantum program. I think it was less than a year later, we announced our first quantum simulator, the ATOS Quantum Learning Machine. And we sold it and installed it at Oak Ridge National Laboratory, which was our first customer. In 2018, we increased our simulation capabilities by adding new features such as noisy simulation, which allows our customers to evaluate the impact of quantum noise on the results of their simulation. Last year, we launched our Quantum QLM User Club, which consists mostly of the QLM users, because we saw that our customers wanted to collaborate using our tool. So there have been 2 editions so far, and it's been quite successful. This year, we've announced the GPU accelerated simulator QLM-E, that I will give you more details on later on, as well as some quantum annealing features, which are now also in the QLM. So we don't only provide gate-based quantum programming tools, but we also provide an environment to prepare code for quantum annealing machines. Tomorrow we will be investing in providing an as-a-service environment to facilitate the access to our simulator, so to our QLM appliance. And ultimately, what we plan to do is, as I said earlier, having a NISC accelerator within our ecosystem. So that should be for 2023. So in order to explain the positioning that was chosen by ATOS, as Xavier mentioned earlier, most players in the quantum hardware field, they have chosen very different technologies. So you've got D-Wave, they are working on quantum annealing machines that are quite advanced technologies and that are dedicated to optimization, to solving optimization problems. IBM, Google, Rigetti, they've been investing in superconducting qubits. Honeywell is promoting trapped ions, and so on. So all of these technologies, of all of them, we don't know which one is going to win the race. So there have been advantages and drawbacks that have been analyzed for all of them. Some of them are linked to scalability, for example, or decoherence. There have been major progresses in all of these fields, but we don't really know at the moment which technology will eventually provide us with fault-tolerant quantum computers. And so all of them, they come with very specific hardware constraints that can be linked to a limited connectivity of the qubits. So that's called topology, or with gate set, the available gate set that is not the same for all of these technologies. So you don't build your programs using the same instructions for superconducting qubits or trapped ions. So what we wanted to do was simplify the process of writing a quantum algorithm and simulating the behavior of this quantum algorithm on any of these hardware technologies using only one environment, which is a quantum simulator. So that's what we call a hardware agnostic approach. And as I mentioned earlier, so all of these technologies, they've got specific programming constraints. And most of the players that have been investing in quantum hardware have provided their own proprietary programming environment that is pretty much linked to the hardware. So what we wanted to provide within the QLM was a universal programming environment that is based on Python, as most of those proprietary programming environments, and that allows our users to just focus on what they want their quantum algorithm to do, and then take into account these hardware constraints. And in order to be as universal as possible, we also decided to develop open source connectors with existing proprietary programming environments in order for our users who previously worked on Qiskit or on Cirq to be able to port their code and use the QLM advanced functionalities. And also, because we know that this is a topic on which research is key, and synergies are key, we also want our QLM users to be able to exchange, to share code with people who are using other programming environments. So this is an overview of our whole ecosystem that is centered on the appliance that you see here. That basically consists in a programming environment that is universal, and where you can find, so it's based on Python, and you can find some libraries and all the tools and all the gates that you want, or you can also build custom gates to write your quantum algorithm. And then you can either just run it on an emulation of perfect qubits, just to see the results of your computation, or if you want to make it more realistic, you can also adapt your code using our optimizers, either topology constraint optimizers, meaning that you just put an oriented graph that represents the topology of the targeted quantum chip in the QLM, and then it will rearrange your code to fit with this topology constraints. Or you can also use our gate set rewriter to adjust to the gate set, the available gate set of the technology that you want to use. And then we have an extensive set of simulators that allow you to scale either up to 41 qubits if you are using a brute force simulator, or up to hundreds of qubits if you're using more advanced ones. And as I mentioned, we've got also this noisy simulation feature that allows you to take some information from let's say quantum hardware providers. Some of them, they put it on their website, and you can put them as an input to our noise model simulator. And then the QLM will provide you with a clearer view on the impact of quantum noise that comes from the quantum hardware on the results of your simulation. So that's very useful for people who really want to eventually run their code on a quantum hardware. And so this is something that I will mention more in detail later on, but we now provide our universal programming environment that is called MyQLM free of charge on our website. And it allows you to use all the programming tools that are within the QLM, except for the optimizers, and to run entry-level simulations on your PC up to about 20 qubits. And within MyQLM, you will find also the connectors with other programming environments as an open source module. So you can also tune these connectors to adapt them to other programming environments that you know, or that could arise in the future. And as this technology is quite new to most of our customers, we also provide expert consulting services on top of that to guide them through the whole process of writing quantum algorithms and then applying them to actual business use cases. Okay, so as I mentioned, this year we also launched a new offer that is actually a GPU accelerated simulator, so a GPU accelerated QLM that is more specifically dedicated at accelerating research on variational algorithms, because the acceleration that is up to 12 times compared to our already optimized simulators. It's limited to 30 qubits, which is actually about the size that is needed for variational quantum algorithms. So really the idea for us right now is to help our users develop algorithms that will benefit from the NISQ era. So we mentioned D-Wave earlier. So that's there are two ways to invest in quantum computing at the moment. You can find two major types of technologies on the market. You've got digital quantum computers that you will program using mostly using gates, quantum gates. And you can also find some quantum annealing machines, such as D-Waves, that actually exploit tunneling effects to run some optimizations. And so these are two technological approaches that we really thought were interesting. So initially, the QLM had covered rather this part of the technological landscape, but recently we decided to also include some quantum annealing features within our QLM. So now, in order to solve or to prepare code to solve optimization problems, you can prepare this code using our QLM for combinatorial optimization option within the QLM. That is a dedicated environment. And you can then either decide to run it or to simulate it using the variational algorithm QAOA, or you can choose to prepare code for quantum annealing and then to run it on quantum-inspired backends, such as simulated quantum annealing or simulated bifurcation algorithm. The interest of using a simulator to prepare such codes is that it's fully tunable, as it's software based, so all parameters can be tuned, and it's particularly efficient. And at the moment, we decided to limit the scalability of our software to 5,000 perfect spins or variables, because it corresponds to the highest number of variables that are actually available on D-Waves machines. But we are thinking about developing a broader offer. So, and I mentioned it also within our QLM ecosystem, we decided recently to provide our quantum programming environment free of charge on our website to foster research on quantum algorithms. And really the target here is really to embed within our community scientists, students, tech enthusiasts, all people who are willing to foster research in this area. So basically, MyQLM consists of the same libraries that are included in our QLM programming environment. So you will be using the same languages. You will find the interoperability kits that I mentioned with MyQL, Qiskit, ProjectQ, and Cirq. And you will also be able to retune it to retune them to depending on your needs. And we also provide an open source simulator, brute force simulator, that is called PyLinag. And you might also be able to optimize it or rebuild it depending on your specific needs. So here is an overview of the ecosystem that we provide with MyQLM to help you connect with a broader community. So you will find a hosted documentation that is quite extensive of the tool on our website. The open source modules for MyQLM are available on GitHub. That's totally standard. If you want to wait before installing MyQLM and play a bit with the tutorials to get a first flavor of the tool, you can also use those tutorials on MyBinder. So that's there's a link in the documentation. We provide, of course, a community forum on Slack to connect to the community and ask questions. And we've got a bug tracker that is hosted on GitHub. And we are planning on releasing articles to inform our community of the latest features of MyQLM quite soon. So the approach, the overall ATOS quantum approach that I mentioned is quite distinct from other approaches that have been chosen for this specific technological area. And the QLM and as well as the consulting services that we provide have received a good success so far. So at first, it mainly came from supercomputing centers such as the DOE labs in the US, but also major centers such as Jülich in Germany, and universities. But what is interesting is that recently we've received also attention from industrial companies, which are willing to invest time and money in this new technology, and they are actually quite active users. I was thinking about Total, which has been a very strong ally in this research field for us, as well as Bayer, with whom we have run a proof of concept on a clinical database search. I also mentioned it, we launched last year our QLM User Club, so that actually stemmed from what we could see was that some of our customers, they were already collaborating and they were publishing together. That was the case for Total and Oak Ridge. And so they were willing to foster synergies with a broader base of QLM users. And so we decided to launch this initiative to allow our user community to connect, to exchange on research topics and progresses around quantum computing. So we've had 2 meetings so far. One of them was in July. We've received very good presentations from Rolls-Royce, for example, and Total as well. And the second one was held last week, and we had a very interesting intervention from a US-based consulting firm that is called Xofia on their work around telco. Okay, thank you very much.